Welcome to the lecture on batch and stream processing, in which we will mainly introduce concepts strongly related to the earth of big data approaches, mainly aiming at processing big data sets. The goals of data processing on a broad level are very similar. Operate over data to increase understanding, surface patterns, and gain insights into complex interaction. As discussed in previous lectures, processing of data generated by IoT devices may take place at different levels, on-board or edge computing, remotely on local servers, or fog computing, remotely on virtual servers and data centers or cloud computing, even combined, nested or hierarchical. These will adopt several different solutions, tools, engines and frameworks depending on the type of and complexity of computation to be performed. To simplify the discussion of these components, we will group these processing frameworks by the state of the data they are designed to handle. Some systems handle data in batches, while others process data in a continuous stream and into a flow system. Still, others can manage data in either of these ways. Batch processing has a long history within the big data world. It involves operating over a large, static datasets and returning the results at a later time when the computation is complete. The datasets in batch processing are typically bounded, representing a limited collection of data persistently and permanently stored in proper storage systems. Very large datasets for which batch operations are often the only option available for processing. Batch processing is well suited for calculation where access to a complete set of records is required, and datasets must be treated holistically instead of as a collection of individual records. This operation requires that state is maintained for the duration of the calculation. Tasks that need vast volumes of data are often best handled by batch operation. That's why batch processing is frequently used with historical data. Handling large quantities of data require longer computation times, since multiple reading and writing operations per task tend to be somewhat slow, being heavily dependent on permanent storage. So, batch processing is not appropriate in situations where processing time is critical. On the other hand, since disk space is typically one of the most abundant server resources, it typically fits well with the parallel programming approaches and models that can handle large datasets through several nodes, such as MapReduce, which can scale to thousands of nodes. Several batch processing frameworks are available, among others Apache Hadoop is the most widely adopted and well-known. Hadoop was the first big data framework to gain significant traction in the open source community. Based on MapReduce model, Hadoop re-implemented the algorithms and component stack to make large-scale batch processing more accessible. The low cost of components necessary for a well-functioning Hadoop cluster makes this processing inexpensive and useful for many cases. Compatibility and integration with other frameworks and engines mean that Hadoop can often serve as the foundation for multiple processing workloads using diverse technology. Stream processing systems compute over data as it enters the system, so it's particularly tailored to time-constrained IoT application. It requires a different processing model than the batch paradigm. Instead of defining operation to apply to an entire dataset, stream processors determine processes that will be used to each individual data item as it passes through the system. The datasets in stream processing are considered unbounded, and therefore the total dataset is only defined as the amount of data that has entered the system so far. The working dataset is limited to the single item at a time. Processing is event-based and does not end until explicitly stopped. Results are immediately available and will be continuously updated as new data arrives. Stream processing systems can handle a nearly unlimited amount of data, but they only process one, through stream processing, or very few, micro-batch processing, items at a time, with a minimal state being maintained in between records. This kind of processing fits well with streams because state between items is usually some combination of challenging, limited, and sometimes undesirable. So, while some type of state management is generally possible, these frameworks are much simpler and more efficient in their absence. This type of processing lends itself to certain kinds of workloads. Processing with near real-time requirements is well served by the streaming model. Analytics, server or application error logging, and other time-based metrics are a natural fit because reacting to changes in this area can be critical to business function. Stream processing is a good fit for data where you must respond to changes or spike and where you are interested in trends over time. In terms of stream processing framework, there are several options available, both freeware and commercial. Most used ones are Apache frameworks such as Storm and SAMSA. Some processing frameworks can handle both batch and stream workloads. This framework simplifies diverse processing requirements by allowing the same or related components and APIs to be used for both types of data. The way that this is achieved varies significantly, and it is mainly a function of how the two processing paradigms are brought together and what assumptions are made about the relationship between fixed and unfixed datasets. While projects focused on one processing type may be a close fit for specific use cases, the hybrid frameworks attempt to offer a general solution for data processing. They not only provide methods for processing over data, but also they have their integration libraries and tools for doing things like graph analysis, machine learning, and interactive query. Relevant hybrid processing system frameworks are Apache Spark and Apache Flink.